Welcome back to the series on statistics. In the last video, I sort of inadvertently, prematurely introduced this topic, but today we're going to be talking in more detail about joint probability distributions. So these are going to be probability distributions that take into account two random variables instead of just one. And as usual, we are going to describe these distributions with probability density functions, the difference being that these probability density functions for joint distributions are going to take into account two variables instead of just one. And so if it's useful, you could think of them as surfaces in three-dimensional space. And so here I've graphed a joint probability density function, this one for two identically normally distributed random variables x and y, each with a mean of 0 and a standard deviation of 1/4. And so this is a graph of what their joint probability distribution looks like. You can see its peak here is at the mean for both variables, and then as you move away from the mean in any direction in 3 space, the probability decreases. And so you could think of it as if you were to integrate under this surface, it will give you the probability. Let's say you were integrating over some bounded region of x values and some bounded region of y values. That will give you the probability of the outcome of x being within that region and the outcome of y being within its respective region. Or alternatively, you could think of it as the probability of the xy pair that results as an outcome of the two random variables being within some range or some area on the xy plane that you're integrating over. And so as with all probability density functions, even these joint probability density functions have to be positive for all values of x, y in the support, because you can't have negative probability. And additionally, if you integrate over all values in the support, you have to get 1. And of course, this is sort of trivially true, because this is telling us that the probability that at least one out of all possible outcomes occurs is 100%. But this is going to hold for these joint probability density functions as well as ordinary probability density functions. So if we're given a joint probability density function, we can derive what are called marginal probability density functions. These are just the PDFs for the individual variables that compose the joint distribution. And they can be derived quite simply by just summing up the joint probability density function over all the possible values of the other variable. And so, for example, if you consider rolling 2 dice, the joint probability density function would just be the probability of the first dice equaling some value and the probability of the second dice equaling some other value. And because these are two independent events, we can just take the product of those two probabilities. And of course, the probability of getting one outcome on a dice, there's one outcome that we're interested in and 6 possible outcomes, that's 1/6, and the product is 1/36. And so this is going to be our joint probability density function. And if you took the marginal probability density function for just the first dice roll, what we're saying here is that this is going to be given by summing over all possible outcomes of the second dice roll. And so, of course, there's 6 possible outcomes here. So if you sum up over the joint probability density function over all these possible outcomes, you'll get 6 times 1/36, which is 1/6. And of course, this is the probability density function, technically the probability mass function, for rolling 1 dice. And similarly, if you were to carry out this operation, but for the second dice roll, you will get the exact same answer. And it's worth pointing out here that because these two events are independent, the product of these marginal PDFs is going to equal the joint probability density function. Now, for dependent events, this is not the case. The product of the marginal PDFs will not equal the joint probability density function. However, you can still derive the marginal probability density functions from the joint PDF, even in instances where the two random variables are dependent. Now, for continuous distributions, the logic is exactly the same, but the equivalent of summing up over all possible outcomes for continuous random variables is going to be integrating. So if you were to integrate over the joint PDF for all possible values of one variable, you would get the marginal probability density function of the other. All right, so just as an example of this for continuous distributions, I'm going to borrow our example from the last video where we were deriving the normal distribution. In that video, we were concerned with the probability of a dart landing in some region of space where we have a dartboard. And so what we established is that we wanted a probability density function that would be centered at the target, which in this case is the origin. And then as you move further and further and further away from the target, the probability of your dart landing in that area would be smaller and smaller and smaller. And what we came up with was actually a joint distribution for x and y, where x and y were both normally distributed. And so that is actually similar to what we see here. The only difference is this has a standard deviation of 1/4. And so as you were to increase the standard deviation, this is sort of spread out the data. And so this is 1/4, maybe 1/2 would look something like this. Looks something like this. And that could be representative of someone who's not as good at darts. Maybe this would be an expert player. The probability is going to peak at the target here and sort of peter out very, very, very rapidly as you move further and further away from the target. But this is actually a good descriptive probability density function for this situation. And in the last video, what we asked was, what is the probability of just the dart landing in some bounded region of x values, irrespective of where it lands with respect to the y-axis? And what we established was, if we have some probability density function that characterizes this situation, you could think of it as a surface above this. If you were sort of to zoom out and look at this from the perspective, like if this was in the xy plane, let's say it was the circle here, this is dartboard, then the probability density function is going to be something like this. It's going to be some surface. And if we wanted to get the probability of the x-coordinate of our dart being within some range of values here, like let's say a or b, we would have to integrate over that surface from a to b. But because we're not interested in the y values at all, we would have to also integrate over all possible values of y. And so what that would look like is it would look like we were integrating underneath that surface over this region here for all possible values of y. And so I'll add some ellipses to indicate that this is for all possible values. And essentially the expression that we derived was we would have to integrate from a to b with respect to x, but we would also have to integrate from negative infinity to infinity, the last situation, with respect to y. And so here we have our PDF with respect to y, with respect to x. And so this expression here, integrating over all possible values of y, we determined that this is going to give us a probability density function for x. And the reason being is because here, what are we trying to figure out here? Well, we're integrating over the surface, so this is going to give us some probability. And we determined that this is going to give us a probability of the x-coordinate of the dart being between a and b. And so if that probability of the x-coordinate of the dart is between a and b is given by this expression, we're integrating over this from a to b with respect to x, then this by definition is going to be some probability density function. And so this expression right here was called the marginal probability density function for x. And you can see this is exactly what we're talking about here. It's derived by summing up or integrating over all possible outcomes of the other variable. Here we're integrating over all possible values of y, and we're getting a marginal probability density function for x. And then integrating over that marginal probability density function from a to b is going to give us a probability of the x-coordinate being between a and b. But just this expression right here in the integrand is going to give us the marginal PDF. And so with that said, let's look at some example problems that involve these joint distributions. So here we're asked, suppose that xy has a probability density function f given by f of xy is equal to x plus y for values of x ranging from 0 to 1, values of y ranging from 0 to 1. We're asked to find the probability density function of x, or the marginal probability density function of x, and the same for y, and then we're asked if x and y are independent. I'm going to do an additional problem here just to see if this is a valid probability density function, but I'm only going to do that with this one, and then we can sort of presume that for the rest of the problems. And so if we want to check if it's valid, let's see, is it valid? Just to remind ourselves what we're talking about. We have to integrate over all possible values. So here it says that our values of x range from 0 to 1, and so do our values of y. So if we integrate from 0 to 1, for x and y, this probability density function, first we'll integrate this with respect to y, and so we'll get xy plus y squared over 2 from 0 to 1. Then we'll integrate the remainder, 0 to 1 with respect to x. What is this going to be? If we plug in y is equal to 0, this whole expression is going to reduce to 0. If we plug in y is equal to 1, we're just going to get x plus 1/2. And so this is the same as integrating from 0 to 1, x plus 1/2 with respect to x. And then what is this? This is going to be x squared over 2 plus x over 2, evaluated from 0 to 1. And of course, at 0, this is just going to reduce to 0. And at 1, this is going to be 1/2 plus 1/2, which is 1. And so if we integrate over all possible values in the support, we get 1. So this is a valid PDF. Now let's try our hand at finding these marginal probability density functions. And so we actually already did this for x, because here in this problem, we integrated over all possible values of y. We integrated the joint probability density function over all possible values of y, and so this is going to give us our marginal probability density function for x. So we determined that this was equal to x plus 1/2. And so our marginal probability density function for x, let's see, is going to be denoted like this, and this is just x plus 1/2. So now let's try the marginal probability density function for y. So write that here. This is just going to be given by integrating over all possible values of x. And so this goes from 0 to 1 as well. We have x plus y with respect to x. This is going to give us the marginal probability density function for y. And so what do we get here? We get x squared over 2 plus xy, evaluated from 0 to 1, which is, and here this is going to be x is equal to 0 and 1. Sometimes you should be careful in notating this. Sometimes I kind of skipped it here, but always remember which variable you're talking about. Here we have 1/2 plus y, and so this is just y plus 1/2. And so it's almost exactly the same as the one for x. And then finally, we're asked, are x and y independent? And it's pretty clear to see that x plus 1/2 times y plus 1/2, the product of the marginal probability density functions, is not equal to x plus y. So that's going to tell us that these are not independent. These are dependent random variables. Now, why exactly is that true? Because for two independent events, the probability of both of those events occurring is just a product. And so if our marginal probability density function is going to give us a probability of x being equal to something, and our marginal probability density function for y is going to give us a probability of y being equal to something, then taking the product of those would give us the probability of x being equal to something and the probability of y being equal to something, which is exactly what's given by the joint probability density function. So if the product of the marginals gives you the joint PDF, then you know that these are two independent events, but in a situation like this, the product of the marginals does not equal the joint distribution, or the joint probability density function, and so we know that these are two dependent events. And so what's worth pointing out is that if I were to give you these two marginal probability density functions, you would have no way of deriving the original joint probability density function in situations where they're dependent. And so there's actually a lot more information encoded in these joint probability density functions, because from these joint probability density functions, as we pointed out in the beginning, you can actually derive the marginal probability density functions for each of these variables, even in situations like this where they are dependent. So this is a good example of that. All right, so here I have another example. For the remainder of these, I'm going to take for granted that these are valid probability density functions. I'll leave that as an exercise to the viewer. It's a good thing to check. It's just to make sure that the area under this curve is always equal to 1 and that this always gives you a positive value for all values in the support. But with that being said, let's find the marginal probability density function for the variable x here. And so that's going to be given by integrating over the joint probability density function for all possible values of y. Here, values of y range from 0 to 1. And so we're going to integrate over 6x squared y with respect to y. So what is this going to be? This is going to be 6x squared y squared over 2, which is just 3x squared y squared, evaluated from y is equal to 0, y is equal to 1. And so this is just going to give us 3x squared. Now, it's important to note here, I didn't note this in the last problem, but I probably should have, that this is going to be for values of x that range from 0 to 1. And so that's an important little note there. This is important for defining this as a valid probability density function. Here, if we were to integrate this 3x squared from 0 to 1, we would get x cubed evaluated from 0, 1, which is just going to give us 1. And so yes, this is a valid PDF, but if we didn't have this condition here, this marginal probability density function would not be valid. And so similarly, let's derive the marginal probability density function for y. It's going to be this right here. We're going to integrate over all possible values of x with respect to x. So here, what are we going to get? We would get 1/3 times 6x cubed y. And so this is just going to be 2x cubed y, evaluated from this time x is equal to 0 to x is equal to 1. And so what is this going to give us? Well, when this is 0, this whole thing is going to 0. When x is 1, we're going to get 2y. We're going to get 2y. And so now for the final part here, we're asked if x and y are independent. As we've established, if they're independent, then the product of the marginals should equal the joint probability density function, or the probability density function for the joint distribution. And so if we took 2y and multiplied it by 3x squared, what are we going to get? We'll get 6x squared y. And that is exactly our joint probability density function. And so yes, these two are independent. All right, I've got two more example problems here for these joint distributions. The first one says that we have a probability density function given by f of xy is equal to 15x squared y, which is very similar to the last problem. It's just a different constant here, but there's another difference here, which goes in the bounds. So we have for 0 less than or equal to x, which is less than or equal to y, which is less than or equal to 1. And so this is a little bit different. Let's see how this affects our answer. And so first, let's try to find a marginal probability density function for x. This will be given by integrating over all possible values of y, our joint probability density function. So y here is going to range from x to 1. No longer are we going to have this very convenient 0 in the lower bound. So we're integrating over our joint probability density function here with respect to y. What are we going to get? We'll get 15x squared y squared over 2, evaluated from x to 1. And this is going to be 15x squared over 2 minus 15x to the 4th over 2. And so what's the best way to factor this? Probably 15x squared over 2 multiplied by 1 minus x squared here. And this is going to be 4. X here is going to range from 0 to y, and y has an upper bound given by 1. And so this is just going to be for x ranging from 0 to 1. Those are all possible values of x here. So this is our marginal probability density function for x. So now let's find our marginal probability density function for y. This here is going to be given by integrating over the joint probability density function over all values of x this time. And so x here ranges from 0 to y, and we're going to integrate over the joint probability density function with respect to x. And so what is this going to give? If we integrate this with respect to x, we'll get 5x cubed y. And we have from x is equal to 0 to x is equal to y. And what is this going to give us? This is going to give us, when x is 0, this whole expression is going to 0. When x is y, we get 5y to the 4th. 4, and then here y is going to range from x to 1, but x has a lower bound of 0. So this is going to be for y on the interval from 0 to 1. So this is our marginal probability density function here for y. And so now here for the last part, we're asked if these two are independent. And so to solve this, I'm just going to take their products, but I'm not going to do that much because I'm noticing that we have 15x squared here, and that appears in our joint probability density function. And I have a y here in the other variable, or the other marginal probability density function. So I'm just going to say that the product of these, so f, the marginal probability density function of y, the marginal probability density function of, I mix these up, but x, if you took the product of these, we'll get 15x squared times y, 15x squared y. And then we're going to get, what's the remainder here? We've got 5y cubed, multiplied by 1 minus x squared over 2. 1 minus x squared over 2. And this is clearly not equal to 15x squared y. And so, of course, these two are not independent because we have this whole giant expression here remaining that prevents this from being equal to the joint probability density function. So x and y are dependent in this example, which is sort of interesting because in the last example, they were not dependent, despite the fact that we had a very similar structure in the joint probability density function. And so it's probably more likely due to the restriction on the bounds here, such that x has to be less than or equal to y, sort of implies some relationship here. But x and y are dependent in this case, as the product of the marginals does not equal the joint probability density function. All right, so this is the last example. This is probably going to be the longest because it involves 3 variables, not just one, or not just 2. And so we're asked to suppose that xy has a probability density function g given by, and this is exactly the same probability density function we looked at in the last example. And that we're also asked to suppose that z has a probability density function h given by h of z is equal to 4z cubed for z on the interval from 0 to 1. But we're also given that xy and z are independent. And so what does this allow us to do? Well, allows us to solve number 1, which is to find the probability density function of x, y, and z. Essentially, if x, y, and z are independent, then we could consider each of their probability density functions as the marginal probability density functions for each of those variables with respect to some joint distribution of the 3. And we know that if these two are independent, then the joint probability density function is just going to be given by the product of these marginals. And so with that being said, we know that number 1, our joint probability density function for all 3 of these variables, let's see, what's a good name for this? I'll just use f, since they use g and h, is going to be f of x, y, z. This is just going to be the product of the marginals in this case. So 15 times 4 is 60. And then we have x squared y z cubed. We have x squared y z cubed. Now we should also note the bounds here. So we have 4, and then we are really just copying and pasting here. So we have for 0 less than or equal to x, less than or equal to y, less than or equal to 1, and z here goes from 0 to 1. So we have 0 less than or equal to z, less than or equal to 1. We can't really throw z into here because we don't have any way of sandwiching z between these two variables. We don't have any relationship between them. And so we kind of have to notate these separately. Now let's solve for the probability density function of xz given this joint distribution here and the fact that all of these are independent. So if we're asked to do this, what we would have to do is we would have to integrate over the joint probability density function for all values of y. And so y here ranges from 1 to x. And so we have the probability, the marginal probability density function xz. This will take xz as argument. It's going to be given by integrating over all possible values of y. Here y ranges from x to 1. So we go from x to 1, 60 x squared y z cubed with respect to y. And so what is this? Thankfully, this is quite simple. We're going to treat all of these as constants, and we'll get 60, or actually we'll get 30. I'll just go ahead and factor that 1/2 into the 60 and leave it as 30. X squared y squared z cubed, evaluated from x to 1. And so what is this going to be at 1? We'll just get 30 x squared z cubed minus, and then here we would get 30 x to the 4th, 30x to the 4th, z cubed as well. And so we could factor out a 30x squared z cubed, and we get 30x squared z cubed multiplied by 1 minus, and here we'd have x squared. And this is going to be 4. Here x ranges from 0 to y, where y is upper bounded by 1. So we have 0 less than or equal to x less than or equal to 1. And z is going to be on the same interval. So, and 0 less than or equal to z less than or equal to 1. So this is our marginal probability density function for x and z. All right, now here we're asked to find the probability density function for yz. So very similarly, if we want to find this marginal probability density function, we just have to integrate over all values of x, the joint probability density function. And so if we integrate over all possible values of x, x here ranges from 0 to y, 0 to y, And we have our joint probability density function of 60 x squared y z cubed. And we're integrating with respect to x. And so what is this going to give us? It'll be 60 x cubed over 3 times y z cubed. 60 over 3 is just 20. So this is going to be 20 x to the third y z cubed. Evaluated from x is equal to 0, x is equal to y. When x is 0, this whole expression goes to 0. And so we get 20 y to the fourth z cubed 4, and let's see here, what's the range for our y and z values? Y is going to range here from x to 1, but x is lower bounded by 0, so we have for y less than or equal to 0 is equal to 1. And where does z go to? Z once again is just bounded by 0 and 1, so z is on the interval from 0 to 1. And so this is going to be our marginal probability density function for yz from our joint probability distribution. All right, so our last problem here is probably going to take the most amount of thought. I'm going to go ahead and clear everything that's not our joint probability density function. So I'm going to make some space here. And I'll do this in purple. So we have our fourth question here is, what is the probability of z being less than or equal to xy? And so this might seem a little complicated at first. I encourage you to pause the video and try this out on your own. Okay, so assuming you've done that, basically we have our joint probability density function here for all three variables. So if I just integrate this from 0 to xy with respect to z, that will give me the probability of z being less than or equal to these. But obviously I need to finish this because this is going to be in terms of x and y, and so I want to integrate over all possible values of x and y, and that's going to give me the probability of z being less than or equal to x and y, taking into account all of the possible values that x and y could have. And so if I do this first operation here, essentially I should write this all out, I guess. The probability of z being less than or equal to xy here is going to be given by, I'm going to have to be very careful how I draw this. We're integrating with respect to z first, but then we want to integrate with respect to, let's see, I'll do x, since x goes from 0 to y. So we'll go from 0 to y there, and then we integrate with y going from 0 to 1. This will cover all possible values. And so if we carry out this first operation here, what are we going to get? Let's make some space. We're going to get the remainder of the integral will stay the same, so we'll go 0 to 1, then 0 to y. Then what are we going to get? Here we'll get 60 x squared y z to the fourth over 4, so that's just going to be 15 x squared y z to the fourth, evaluated from z is equal to 0 to z is equal to xy dx dy. And so if we go down a little bit, what is this going to be? If you plug in xy here, we're just going to get x to the fourth, y to the fourth, and you add those to the exponents. All we're going to get is, rerunning the rest here, 0 to y, get 15, and then we'll get x to the 6th. Oops. Then we'll get y to the 5th. And now we want to integrate this from 0 to y with respect to x. So carrying out that operation, get to go from 0 to 1. What are we going to get here? We'll get 15x to the 7th, y to the 5th. Then we're going to integrate from 0 to y, and x is 0. This whole thing will go to 0, so we'll just plug in y there. And so we'll get 15. We'll have y to the 7th, y to the 5th, so it's just going to become y to the 12th. And then we're dividing by, we went x to the 7th over 7, so it's going to be a divisor of a factor of 7 here. And then finally, we need to integrate from 0 to 1 with respect to y. And so what is this going to give us? Here, we're going to have to, this should be 12. Not 15. I don't know why I wrote that. I definitely said 12. This should be a 12. And so if we integrate this with respect to y, we're going to get, let's see, 15. And then we're just going to have y to some power, but y is going to be evaluated at 1 and 0. When y is 0, it's going to go to 0. When y is 1, it's going to go to 1. So I'm just going to leave this off. This will be 15 over 7 times 13. And so that's going to reduce to 15 over 91. And so this is going to be our total probability of z, the random variable z, being less than or equal to the product of the random variables x and y. And so this is how you would go about solving that problem there. Now, in the source for all of these problems, I got this from the Statistics Libre text. They actually got 15/92. I'm just going to assume that that's an error because I have no idea how they could get to 15/92. I'm assuming that they tried to write this down and just miswrote it. But if anybody thinks that this is wrong or I've done this incorrectly and that the answer actually is 15/92, please let me know in the comments. I would appreciate that. But that's going to do it. Those are my 4 examples of joint probability distributions and marginal probability distributions, or marginal probability density functions from joint probability distributions. We talked about independence of the random variables that makes up the joint distributions. And so I hope this was informative. I hope you guys can use this. Thank you all for watching. I'll see you in the next video.